In this video, we'll be covering 8.3 and 8.4. 8.3 covers the product and quotient theorems. Here's the product theorem first of all. I know that looks a little overwhelming, but what it's basically just saying is that if you want to multiply two complex numbers together, then first put them into trig form, and then once you have them in trig form, you simply multiply the radii together, and then you take the cosine plus I times the sine of the sum of their angles. So we can look at number 12 now. Notice that both of our numbers are already in trig form. So now we just need to multiply the two radii together, 8 times 11, which is 88. And then we need to take the cosine of the sum of the two angles. 59 plus 117 is 176. And sine of 59 plus 117, so again 176. And then we get it right. Yay! So 88 is simply the product of 11 and 8. And then the 176 number that we see here for both cosine and sine is simply the sum of the two angles. So then this next brings us to the quotient theorem. And the quotient theorem is analogous. Instead of multiplying the radii, we are taking the quotient of the radii. And instead of adding the angles, we are subtracting the denominator angle from the numerator angle. So now we can look at number 13. So we're finding the quotient of z1 and z2. z1 and z2 are both already in polar form. So notice here that we have 14 for the first radius and 5 for the second radius. So the beginning of this formula, and here we're dealing with the compact form. So just to review the compact form again, you can see here that we have still the ratio of the two radii, and then we subtract the second angle from the first angle, the second angle being the denominator angle. So 14 divided by 5. And then 81 minus 115, negative 34. So we submit that and we got that right too. So you can write 14 over 5 or 2.8 because you're not rounding. If your denominator though is something other than 2, 5, or 10, you're going to want to just write it as a simplified fraction. And then 81 minus 115 is negative 34. And that's it for 8.3. So now we get to transition to 8.4. 8.4 is a harder section. We are covering De Moivre's theorem and powers and roots of complex numbers. So let's start with De Moivre. So for De Moivre's theorem, what we have is r cosine theta plus I sine theta. So that is a complex number written in trig form. And we want to raise that complex number to the nth power. And this would be like a generalization of the product theorem. So you have r raised to the nth power, as you would expect. And then n times the angle. And here's the compact form of it. So now I'd like to show you my open math problems 14 and number 16. Starting with number 14, here we have a complex number that is already written in trig form. So what we need to do is simply take the radius, which is 5, and raise it to the 5th power. And then we are going to multiply this by cosine 5 times 120 degrees plus I sine times 5 sine of 5 times 120 degrees. Notice that the 5's here are from this 5 in the exponent. And then this would further simplify to 3,125 CIS 600. This is the compact form. 600 is coterminal with 240, so we could rewrite this as 3,125 times CIS of 240, and then this becomes 3,125 times negative 1/2, which is the cosine of 240 degrees, plus I times negative root 3 over 2, which is the sine of 240 degrees. And then we can further simplify this. So then notice here that I've moved the I to the right-hand side so that now my answer matches the A plus BI form. To complete this problem, you then want to take each of those two numbers and put them into your calculator and round to the nearest tenth. Of course, in the first one, you don't need to round. That one already just truncates at 0.5. But then we take this value and multiply it by the square root of 3, and we get this value here rounded to the nearest tenth. For this next question, number 16, I'm going to do this one on the board because it is a longer question, and here you can see the full picture of de Moivre's theorem. So for number 16, we're looking at the imaginary number, or the complex number rather, negative 2 plus I raised to the 7th power. To evaluate this, or to simplify it, we are going to use de Moivre's theorem. First, we need to take this number and turn it into trig form, trigonometric form, or polar form. So to do this, we need to figure out what the radius is and what the theta value is. So first, we want to recognize that the number negative 2 plus I is located right here in the second quadrant. The radius is just going to be the hypotenuse of that right triangle that has legs of length 1 and 2. So the radius is simply the square root of 5. For the angle is going to be a second quadrant angle, and we can find it using the tangent of y over x. Now that value on the calculator will end up being in the fourth quadrant. It will be a negative value in the fourth quadrant on the calculator. Now at this point you might ask, should I be in radians or should I be in degrees? It doesn't matter. You can choose, because in the end, after you are in trig form, you're going to convert back to this format, the A plus BI format. So you can choose to use trig, you can use polar, or you can use radians or degrees. Sorry, I'm jumbling my words here. So what I want to do is I want to check my mode and just see where I'm at. Okay, I happen to be in radians, so I will go ahead and stay in radians. And when I take the tan inverse of negative 1/2, I end up with a theta value of 0.4636, etc. This would be a fourth quadrant value that's negative. So if I add pi onto it, something from here added pi onto it would put me up in the second quadrant. So then that gives me 2.6779. Now, as much as possible, you want to use an unrounded version. In fact, just keep using the number on your calculator, because if you round and then you raise that to a certain power, or you then multiply it by a certain number, you're going to amplify how much you rounded by. You will amplify your rounding error. So just keep this long decimal number in your calculator and use that number. Okay, so then what we have here is we can rewrite this as square root of 5 CIS 2.6779 all raised to the 7th power. Now, I like the compact form because it's a whole lot less writing. So hopefully you can feel comfortable with the compact form too. So then what we do is we apply the 7th power. This is where we apply De Moivre's theorem, now that we have it in trig form. We apply the 7th power to the square root of 5. And then for the radian number, we want to multiply that radian number by 7. So just to remind you of what I am doing, here is De Moivre's theorem. So I had already switched it into polar form or trig form. And now I am taking the radius and I am raising it to the nth power. And then I am multiplying the theta value by n. Okay, so then what that does is that gives me the square root of 5 raised to the 7th power. So that's approximately 279.508. And then I have CIS times, and remember I'm using the calculator button here, 18.7456. I'm using the answer button on the calculator is what I'm saying. From back when I had this long number on the calculator, I then multiplied that long number by 7, and that's why I keep putting ... It's because I'm using the long form version of that number that's on my calculator. Okay, so remember that this is in radians. My calculator mode hasn't changed, so I'm going to continue to address this in radians. If you had done this in degrees, then you would need to have a degree symbol. In each of these cases, you would have a degree symbol. So now I'm going to multiply this number right here times the cosine of that number right there. So now you are not required to write that out. I just wanted to not lose anyone as to what I'm doing. I'm taking the number out in front, and I'm using the distributive property. First, I'm going to multiply it to cosine of my new angle, and then I'm going to add that number times sine of my new angle, and then I have that I value right there. So it's kind of fun that a number like this starts out nice and pretty, then ends up being really yucky, and then turns back into the minus 29i. Perfect. All right. So we've already looked at De Moivre's theorem, and now we're going to look at powers and roots of complex numbers. So powers and roots of complex numbers is the generalization of De Moivre's theorem, because you're taking the 1 over n power, which would be the nth root. So you're going to apply the same thing as you did with De Moivre's theorem, except then you also have to generate an extra number of answers. So let me explain this specifically then at number 17 and number 19. Here let's start with question number 17. Find all complex square roots of 16. Now you and I both know that the square roots of 16 are positive 4 and negative 4. Those are the two roots. You've got your principal square root of positive 4 and your negative square root of negative 4. But we're going to take something that's very easy to do and use a complicated theorem so that you can understand the complicated theorem a little better. And then that will help you with being able to do this problem. Okay, so first what we want to do is we want to revisit the nth root theorem. And we're going to go ahead and see the number 16 needs to be written in trig form before we get started. This theorem uses degrees in this version of this theorem, so I'm going to go ahead and use degrees as well. So let's note that the number 16 is on the positive x-axis in the complex plane. It's at 0 degrees. Of course, the radius of something on an axis is just going to be the length of that vector. And so we have 16 CIS 0. And we're looking for the square roots. So we have 16 CIS 0 raised to the 1/2 power. And so then you can see that this would be applicable for, you can use de Moivre's theorem. But we're doing more than just de Moivre's theorem because we need to find both routes. So de Moivre's theorem will, both roots. De Moivre's theorem will give us the first root, and then we're going to find the second root using the nth root theorem. So using de Moivre's theorem here, we end up with 16 to the 1/2 times CIS of 1/2 times 0 degrees. So, of course, 16 to the 1/2 power is 4. And then we have CIS 0. So that is the same thing as 4. The square root of 16, the principal square root of 16 is 4. And there it is. So there's the first one, and now let's look at the theorem again so we can find the second one. To find the second one, we need to generate all possible values to n minus 1, okay? And k is going to start with 0, and since our n value in this case, we're looking for the nth root, which would be, in this case, the square root, so n is 2. That means our k values are going to be 0 and 2 minus 1, 1. So we're going to generate these alpha values. Any occurrence of n in this formula here is going to be replaced with the number 2 because we're looking for square roots. So what that looks like here is that alpha is equal to theta plus 360k divided by 2, and your k values are going to be 0 and n minus 1, or 2 minus 1 is, ask what is the theta value? The theta value in this formula is the original theta before you raised it to a root, or before you took the root of that value, before you raised it to a power, and that would be 0 degrees. So we want to replace each of these occurrences of theta with 0 degrees. So 0 plus 0 divided by 2 is 0. And 0 plus 360 divided by 2 is 180 degrees. So these are going to be the alpha values. Now, what are the alpha values in the formula? If we go back to the formula, we see that we are going to be generating multiple roots based off these alpha values. So each of them will start with the nth root of r, which in our case is the square root of 16, or 4, followed by CIS of our two alpha values. So that means that for our problem here, what that means is we have 4 CIS of the first alpha value, 0, we already found that one. And then the second one is 4 CIS of the second alpha value, which is 180 degrees. So going back then to my open math, we are giving our answers in trig form with angles in degrees and roots separated by commas. So we have, instead of writing 4 CIS 0, we're writing 4 times cosine 0 degrees plus I sine 0 degrees. And instead of 4 CIS 180, 4 cosine 180 degrees plus I sine 180 degrees. Okay, now for question 18, this is a great question, but the video explanation is also excellent. So that means that if you can watch this video and listen to his explanation, hopefully between my explanations given to you for 17 and 19 and his great explanation for 18, you'll have 2 different people explaining the same concept to you, and hopefully that will round out your understanding. So do use this video help right here for question 18. And let us go on to question number 19. Here we're going to find all complex solutions of this right here. Now if we were to do this kind of problem using algebra, we would say, okay, that would mean that I need to get the 8 on the other side, and then I would need to take the cube root of both sides. So I go and take the cube root of both sides. That's kind of a light color. Sorry about that. So anyway, that ends up being x is equal to 2, which is great, except that it's only one of the 3 roots. There will always be the same number of roots in the complex plane as you see for this number. Now let me show you something really cool. Here's the complex plane, right? Here is the number 2. The number 2 is right here. Where are the other 2 solutions going to be? The other 2 solutions are going to be other spokes of a wheel, where each of the wheels is 120 degrees apart from each other. This is another way of seeing the nth root theorem, but seeing it visually. If my explanation on the previous one was a little difficult, you can see it visually here. So if I were to take 120 degrees between these 2 vectors, and then 120 degrees again between these 2 vectors, then it would be another 120 degrees to get around the full circle. Now I know that there's 120 degrees because I know that I'm looking for a total of 3 roots. And if I'm looking for 3 roots, then I'm going to take 360 degrees and divide it by 3. If I was looking for 2 roots, then I would divide it by 2. And that's why back in the previous problem, our alpha values were 0 and 180, because you take 360 and divide it by 2. In our case, our alpha values are going to be 0, 120, and 240. Those are our alpha values for this problem. So you can use the nth root theorem, but I prefer using this visual diagram because I like to visualize math. I like to see math. If I have to memorize things in a formula, then I don't usually remember them. But when I can see the math, then it makes a lot more sense to me. These complex answers are all part of a circle, and each of these spokes of this circle are going to be exactly the same number of degrees apart from each other, and then they all will have the same radius length. That makes sense. So we're going to find all of these by using the De Moivre's theorem for starters. De Moivre's theorem says that we take 8 and we rewrite 8 as 8 CIS 0. And then we raise that to the 1/3 power. That's going to be the cube root of 8 written in trig form. So then that ends up becoming 8 to the 1/3 times CIS of 1/3 times 0, which is the same thing as 2 CIS 0. Now I already knew that 2 CIS 0 was one of the answers because I know that by solving this algebraically, I get x is equal to 2. If you're doing this problem up here, you can't just intuit from algebra 1. You're going to have to use you have to use the De Moivre's theorem in order to do that one. Okay, so that's the first answer. I don't know why I wrote equals again. Now my other 2 answers are then going to be 2 CIS 120 and 2 CIS 240. And I got these values from my wheel over here, right? 0, 120, and 240. So why bother to write this format if by looking at the wheel I can see that these are the answers? Only just to remind you that this sort of format is going to work for more complicated situations like number 18 that you can't do in your head. Alright, so here you can see your answers are written then in trig form, which is very nice. But in case you wanted to know what those answers are in real life, not in real life. I meant in rectangular form. You have 2, and then this one is going to be 2 times the cosine of 120 degrees. Cosine of 120 degrees is -1/2, so that would be -1 plus the square root of 3. So this is the square root of 3 over 2, and then when you multiply the square root of 3 over 2 times 2, you just get the square root of 3, I. And then over here you have cosine of 240 degrees, which is again -1/2, so -2. And then sine of 240 degrees is -√3 over 2, so when you multiply that by 2 is just -√3. This is supposed to be a 1. 2 times -1/2 is not 2, it's 1. -1. I. And those were those vectors on the pinwheel. Here's 2. This one right over here is -1 plus √3i. This one down here is -1 minus √3i. So that's really cool. I think this is quite exciting.